Okay, thank you for the introduction. And firstly, I would like to thank the scientific committee for having invited me to give this talk about quantum interferences in atomic ionization by 1 and 2 color laser pulses. Let me introduce this talk with the most relevant experiment that stresses the difference between quantum mechanics and classical mechanics. And this is the double-slit experiment. And I should thank the speaker of the last session in the morning that he spoke about this, and mainly, or especially, telling about the debates between Niels Bohr and Albert Einstein. So I will skip all of this, and I will focus on the experiment performed by Klaus Johnson about and what he did is he threw one electron at a time, and he observed kind of interference pattern here through a statistical collection in the measurement process. So this experiment was chosen as the most beautiful experiment by the readers of the physics world in 2002. So quite schematically, if we have only one half cycle, we will have ionization near the top of this cycle, and the wave packet will be emitted to the left. The action of the second half cycle will be to bend this wave packet and throw it to the right. But there will be another wave packet released near the bottom of the electric field, and this wave packet will also go to the right. So these two wave packets will interfere. So the question that naturally arises now is, can we generalize this very naive picture to some experiment in photoionization? Or moreover, can we have double-slit interference in one photoionization experiment? Okay, I will anticipate the answer. It is yes, and I will try to convince you of this during the talk. So this is the outline of my talk. Firstly, I will mention how the electron yield can be obtained through a very simple semiclassical theory. Will we identify the different interference patterns that we find there, and we will see that the double-slit interference pattern will arise quite naturally. We will see the effect of the tail of the Coulomb potential on these electron interference patterns. And in the end of my talk, I will show you a couple of experiments with 2 color lasers. So this is the Hamiltonian of the atomic system in the single active electron approximation. This is the potential of the central potential of the atomic system, which is subject to a laser field linearly polarized along the z direction. The momentum distribution can be calculated through the transition matrix, and there are different methods in order to calculate this matrix. I will just mention the semiclassical method, where the transition amplitude from one initial state to a final state in the continuum can be regarded as a coherent superposition of several electron trajectories. And these electron trajectories are born in one ionization time tr and with final momentum k. Each of these electron trajectories has one weight given by the ionization amplitude g and one phase given here by the Volkov action S. So how can we calculate these ionization times? We can do it through the simple impedance model, which considers that the velocity at the exit of the tunneling is 0. So from here, we can just extract the value of the ionization times. Of course, there are other more complicated ways to do it, more sophisticated theories which involve complex times. But this is enough for now. Let me now show you one simple example for one sinusoidal electric field here in black. But what is more important is the vector potential here in red. So every time that the vector potential crosses the line minus k, we have a solution. So we can observe two solutions per optical cycle or unit cell, these two here. The early release time, here marked with a circle, and the late release time, here marked with a triangle. The separation in time of these two slits is less than half a laser period. And for an infrared laser, this is less than 1 femtosecond. The interference of these two trajectories will give rise to the intracycle interference, or the double-slit interference. On the other hand, the interference of the trajectories at different optical cycles will give rise to intercycle interference. Now, skipping some algebra, and after a few approximations, the momentum distribution can be written as the equation of the diffraction grating, but now in the time domain. I don't know if you can remember this type of equations can be found in any books about optics. And the probability could be split in two different factors. Here is the intracycle factor. This means the factor stemming from the coherent superposition of the two electron trajectories within the same optical cycle. And here, this other factor comes from the interference of the n different slits or the n different optical cycles. So let me mention this factor first, that I call B. When the number of cycles goes to infinity, this factor transforms to a sequence of delta functions. And the positions of these delta functions is given by the conservation of energy for the absorption of multiple photons. The width of each peak, here delta E, and the time duration fulfill the uncertainty principle. Just for the sake of completeness, let me tell you that this delta S is the accumulated action between the early and the late release times. And still the here is given by this expression, where UP is the ponderomotive energy and IP is the ionization potential. This equation can be generalized to other types of pulses, not only for sinusoidal pulses. So here I plot, we are dealing now with a two-dimensional problem because this process has cylindrical symmetry around the polarization axis. So we need two different physical magnitudes in order to describe the final state. So here we choose the longitudinal momentum along the polarization direction and the transverse momentum. So here in this plot, in the figure A, we show the intracycle factor. So you observe some stripes here, rather vertical, but tilted also. And here in figure B, what you can observe is the intercycle interference pattern. And these are essentially the multiphoton or ATI peaks that in the momentum distribution became ATI rings. And the contribution of the momentum distribution will be the multiplication of these two that I plot here. So you can observe that you can see very easily the multiphoton rings, and superimposed, you can observe also the intracycle interference pattern. So these calculations were performed within the semi-classical theory. What happens when we compare with TDSC calculations? So here I have the semi-classical the result, and I compare with TDSC calculations. You can observe more or less the ATI rings, and also this intracycle interference pattern is very well observed. And of course, there are some difference between this plot and this plot. In the semi-classical theory, I haven't considered the contribution from rescattering electrons. And apart from that, there are some structure here near threshold which can be explained beyond the strong field approximation. So let's focus now on this structure. Here we have this structure similar to a fan that Spanish women are used to using or in order to remove the heat from their faces. And the number of nodal lines is equal to the dominant angular momentum of near-threshold electrons. And how can we understand it? What is the origin of this structure? The origin of this structure is the coherent superposition, is the interferences of many trajectories released at different released at different times, and they are all interfering, and these trajectories are oscillating along a Kepler orbit. And as these Kepler orbits, as the angle of this Kepler orbit changes, this interference moves from constructive to destructive interference. That's why we can observe here this pattern. So with some classical help, I mean some classical things, we can obtain this expression for the dominant angular momentum as a function of the nuclear charge of the remaining core and the quiver amplitude, alpha. This quiver amplitude is given only or depends only on the laser parameters. So in this sense, we can say that this expression is rather universal because this is independent of the atomic species. So another effect of the Coulomb potential is the following one. Here I plot the photoelectron distribution along the polarization axis in the forward and backward direction. And I do it within some approximated approach here within the Keldysh-Faisal-Rice approach. Here, phi I is the initial state, and Kf is the final channel. If we vary the nuclear charge of the final channel, as we are doing here, we can go from the strong field approximation on the top to the Coulomb-Volkov approximation at the bottom. The Coulomb-Volkov approximation considers the action of the Coulomb potential non-perturbatively. Of course, it does it approximately. So we see that as the strength of the Coulomb potential increases, there is a monotonic shift of this envelope. And this envelope corresponds to the intracycle interference pattern. On the other hand, we observe that the position of the intercycle or ATI peaks here are the same. They are completely unaltered. So now let's go to the last part of my talk, which I will mention two different experiments with two colors. One color has a frequency that is the double of the first one. And by changing here the relative phase between the two colors, we can shape or sculpt the laser pulse. So firstly, I would like to show you one experiment performed for single ionization of helium atoms. This experiment was performed in the Photonics Institute at the Vienna University of Technology. And here the intensity of the two colors is about the same. And they have measured the longitudinal momentum distribution as a function of the two color phase. Here you can observe these structures. The structures here in color red, they are coming from the intercycle pattern. They are ATI peaks. On the other hand, these structures with the shape of fingers, here, or here, or here, they are coming, the origin of these are intracycle or double slit interferences. So this second pattern, the intracycle pattern, is more evident for two color phases equal to multiple of semi-integer values of pi. So here, for example, I show that for pi over 2, this momentum distribution. And these steps here are evidence of these double slit interference structures. So, and on the other hand, when some momentum distributions are shown for 0 or for pi, so you observe these peaks, but these peaks correspond to ATI peaks. When we compare with some calculations, TDSC calculations, here we observe without any doubt that the experiment or that the TDSC calculations fits the experiment very well. So we don't have any doubt about the origin of these oscillations here. So let me now show another experiment. This experiment is for single ionization of argon. Was once performed at the Max Planck Institute in Heidelberg. Here, the intensity of the second color is about 1/10 of the intensity of the first color. So you can observe that the symmetry was broken. So we have more ionization to the right or in the forward direction. This happens for two color phase equal 0. But what happens when we vary, or when they vary, the two color phase? You can observe some motion from ionization going from the right to the left. So in this way, we can control in which direction the ionization will be mostly produced. So we have produced some calculations about this, some TDSC calculations, and some classical calculations. Of course, the TDSC calculations show a lot of some rich structures, as we have shown, as I have shown before. And these structures are not present in the classical calculation as expected. But the asymmetry of the distribution is quite well tracked by the CTMC calculation. So in some sense, we can say that we have some degree of quantum classical correspondence. But if we want to stress this quantum classical correspondence, we have plotted also the distribution, the final distribution, as a function of the kinetic energy and angular momentum of the electron. And of course, there are some structures in the TDSC calculation, for example, these horizontal stripes, and which is a signature of multiphoton absorption, which is not present in the CTMC calculations. Even though the general appearance is more or less conserved. And this is also moving for when the two-color phase is changing. So some of these structures, I will not describe them here, but we have submitted one proceeding in this conference about some of these structures. So now, at the time of comparing experiment with theory, we have to do some intensity averaging over the focal volume for the TDSC calculations. So you can observe that the similarity is outstanding here. And this is for phase equal 0. This is for two-color phase equal pi over 4, pi over 2, 3/4 of pi, and pi. You can observe as the wave packet moves from forward emission to backward emission. And again, the similarity is very good. And other thing here to highlight is that the two-color phase here, which is a priori unknown in the experiment, can be determined by comparing theory with experiment. In experiment, they can manipulate the differences of the two-color phase, but the absolute value cannot be handled in principle, only through a comparison with theory. So I have reached to the conclusions. Firstly, I showed how this Dawes-Licht Young-type interference naturally emerges for a photoionization process. And we have seen how the Coulomb potential of the remaining core affects this intracycle pattern. Especially, this is crucial for the formation of the near-threshold bouquet-shaped structure. I also show you two different experiments with two-color lasers, and where the intracycle interference pattern could be measured and enhanced. And I have very little talked about quantum classical correspondence. What are our plans for the future? We are trying now to include some of these coherences through the action in a CTMC code. We are also now working about calculating a second term in the Coulomb-Volkoff approximation, a term corresponding to rescattering, to rescattered electrons in order to cope with rescattering. And maybe we can see some interferences, not only among direct electrons, as I have shown, but also between direct electrons and rescattered electrons. And also, we are working on a protocol about how to determine the time delays using two-color laser pulses. So this work wouldn't have been possible without the collaboration of some people. Let me just mention the group of Joachim Burgdorfer at the Institute for Theoretical Physics of the Technical University in Vienna, the group of Markus Kissler, these are experimentalists, the group of Markus Kissler at the Photonics Institute in the same university, especially Xinhua. Also the experimental group in Max Planck Institute, the group of Robert Motthammer, especially Nicolas Camus, Kenichi Ishikawa from the University of Tokyo, Xiaomin Tong from Tsukuba, and Sebastián López from IAFE Buenos Aires. So thank you very much for your attention.